Hello, everyone. Welcome to today's Yabo session, where we will be just doing revision on some of the last few topics that you have covered as you prepare for your final exams. So I'm not gonna waste much time. I'm just gonna go through some important information with regards to the sections highlighted, which will be looking at momentum, rotation about a fixed axis, angular momentum, circular oscillatory motion, that's planetary motion, and equilibrium, which is which will be looking at balancing of forces, static equilibrium for inclines and different systems, especially the case of the ladder that is basically um, sort of inclined towards a wall. So you have seen most of these questions. I'm just going to be highlighting on the important information you need to remember as you work with these problems. So the first question we have here is basically a simple question on momentum, where we have a car A, rear ends car B, which has twice the mass of A. So we have two cars in this case. It's also always important to have a picture of what's happening. So here in this case, we have our, sorry, let me, okay. So that will be car A, and we have car B there. Okay, so those are the two cars. So car A has mass m and is moving at a velocity v, I think, according to that question. And this is on an icy road. So that statement is to try and tell us we should ignore friction in this case, so that and the speed is low enough so that the collision is essentially elastic. You should know the properties of an elastic collision for you to be able to answer that question. Car B is stopped at a light when it is struck. So the collision there is because car B stops at a light and car A hits the rear of car B. So now car A has a mass of m and a speed of v before the collision. So what happens after the collision? And according to this question, we cannot know the action of or the events that follow after collision, or the parameters that relate to the event, without analyzing the collision itself. So the options there, each car has half the momentum. We need to ascertain that. We need to get a basis for that reasoning. Or car A stops and car B has momentum mv and all the like. So car A stops and car B has momentum 2mv. We need to check that. Or the momentum of car B is 4 times as great in magnitude as that of car A, or each car is half of the kinetic energy. So knowing that this is an elastic collision, the properties you already know, characteristics of an elastic collision will conserve both momentum and kinetic energy. So that means if this is 2m, so initially v is 0 and mass is okay, and the mass is 2m. Okay, so big M is equal to 2 times small m, like that. So now, conservation of momentum. By conservation of momentum, we have mv equals to m times v a. So we will call this va final, plus 2m times vb final. So vb and va. So va initial. So remember, anyway, let me just write everything in full so that No one is left behind. Okay. So this is plus 2m times 0. Remember the initial speed or velocity of car B is 0. So we just include it like that. I skipped it because it's 0. Anyway, so this is our equation for the momentum, conservation of momentum. Total initial momentum equals to the total final momentum. So simplifying this, let me make it nicer, gives us m times VA equals to m times VA final plus 2m times VB final. So the m out, it leaves us with a simple equation, V. So VA initially is equal to V. So we're told this is V, so we can express in terms of V. So we can now say V equals to VA final plus 2VB final. So this is our first equation, which is based on conservation of momentum. The second equation should be conservation of kinetic energy. As such, half mVA initial squared plus 0, because VB initial is 0. I'm going to leave that one out. Will be equal to the total final kinetic energy, which is half mVA final squared plus half 2m VB final squared. So according to what we have here, we can eliminate the m. Then we have half VA. VA initial we said is V, so we can simplify that. Half V squared is equal to half V, or we can even remove the half. It's common everywhere. Equals to VA final squared plus VB final squared. Okay, so now to solve, we can eliminate we can eliminate which one. So we want to find either, so that we can compare the two. So we can eliminate VB final or VA final, whichever. So VA final, according to this, VA final is equal to V minus 2VB final. Such that we've got V squared equals to V minus 2VB final, everything is squared, plus VB final squared. Okay. So this leaves us, let's try to solve that one. V squared is equal to, squaring this gives us V squared minus 4VB final times V plus 4VB final squared. I hope I did that right. So plus VB final squared. Okay, so that simplifies the problem for us because if we can remove this bracket to just confuse things. So we've got V squared and V squared there. So this V squared comes this side. We've got 0. 0 is equal to so 4VB squared plus a VB final. So we've got minus 4VB final multiplied by V plus 5VB final squared. And factoring out VB final, we get 5VB final minus 4V. So that means VB can either be 0 or 5VB is equal to 4V. So that is, if this is 0, this expression can only be 0 if either VBF is 0 or 5VB final is equal to 4V, right? That also gives us 0. So that means VB final will be 4 over 5V. Okay, so if that's the value of VB final, what is VA? Remember we had VA here. VA final is equal to V minus 2VB final. So VA final equals to V minus 2VB final. V minus 2VB final, which is equal to V minus 2 times 4 over 5V. So what does that mean? This is V, which is 5 over 5V minus 8 over 5V, which gives us minus 3 over 5V. I think something is not right. What did I do wrong there? Yes. This is VA squared equals to VAF squared plus 2VBF. There's a 2 there. I left that 2 down there. So these 2 should come back here. Let me change the color and correct. So it is this 2 which was missing. We add it back there. What does it mean? We have 2 there. And 4 plus 2 makes this one 6. And that's 6 there. That's 6 there. And 4 over 6. So this is 2 times 4 over 6, which is 2/3. So I have to change this. 4 over 3. 4 over 3, and this will be 3 over 3, making this minus 1 over 3. Okay, so it means this is 2 over 3V. This is minus 1 over 3V. So these are the velocities, VA final and VB final. VB final is twice in magnitude to VA final. So now each car has half the momentum. So we can't say half the momentum because initially B is 0, but we see B having a momentum that A is out. Then car A stops. Car A has not stopped because car A is moving in the opposite direction at with 1/3 its initial velocity. So B and C are out, they're about stopping. Then the momentum of car B is 4 times as great in magnitude as that of car A, and each car is half of the kinetic energy. So we need to check those two facts. So if the momentum there will be M, final momentum, P final for A is equal to M times 1/3 V with a negative there, which is mv over 3. Negative in the opposite direction. Momentum for B is 2m times 2/3, I think. Yes, 2/3 V, which is equal to 4 mv over 3. So in terms of magnitude, PBF, final momentum, is equal to 4 times PA final. The momentum is 4 times according to what we have there. So that's how D is correct. And each car has half the kinetic energy, as half of the kinetic energy. So the kinetic energy initially is 0, so that doesn't apply to B. And as well as half mv squared for the first one will not give us half of the kinetic energy there when V reduces to 1/3. So that expression is out. So D is our correct answer. Okay, so it's 4 times. That's how we check. So anyway, well, besides the question not having any answers to do with calculations, to check those facts, you just need to apply, know what your elastic collision is all about. Then you properly apply your equations for the conservation of momentum first, and also for the conservation of kinetic energy. So that's what is important with this part. You should know what an elastic collision is, what an inelastic collision is, and just apply the facts as you know them. Okay, so that's the first part. I'll just rush through the second one. We've already changed from momentum. We're now on the second part, a question from rotation about a fixed axis. So most importantly, you should, if you are familiar with your equations of motion, this section should not give you a problem. So remember, for your equations of motion, you've got acceleration. Should I use acceleration? Equals to what is that? Velocity V final minus V initial over time, from which you get the equation V final is equal to V initial plus acceleration times time. Okay, so usually that's our first equation. Okay, I think I need to save space there so that I can. Okay, then from there we have an equation that is in terms of V squared, V final squared is equal to V initial squared plus 2 times acceleration times the displacement, right? Then we've got one for displacement, S being equals to VIT plus half acceleration times t squared. Then we've got the last one, the most interesting one, also for S, which is average velocity, V initial plus V final over 2. That's how you get your average, and you just multiply this by time. So basically this gives us the four basic equations. The four basic equations. 1, 2, 3, 4. Everything else is a derivative of these equations. And you have these equations given anyway in your formula sheet. So you should be familiar. What is important is for you to know how to use them, given the information the question requires you to find. So now the analogy, when we look at motion about a fixed axis, like you see a wheel rotating about a fixed axis like that with constant angular acceleration. So our acceleration changes to be angular acceleration, which we represent by alpha. And this will be omega final, which is the angular velocity. Final angular velocity minus initial angular velocity over time. Time doesn't change, right? So this is how the equation changes in this domain where we're looking at rotating bodies about a fixed axis, such that our omega final angular, I think it's nicer if I do this. So from there, we have this omega final is equal to omega initial plus alpha t. That's the equation for angular velocity, final angular velocity. Omega final squared is equal to omega initial squared plus 2 alpha theta. So now already you can see in terms of our displacement is an angular displacement, which is theta. So remember, theta is just the angle covered, such that omega is d theta dt. Just like your s can be dv dt, right? But at times it's not just as simple as that. That would be if you don't have acceleration anyway. You would simply give it in terms of the rate of change of displacement. That's your velocity. Okay. So s is the displacement, theta is the angular displacement. So it's they're related like that. And so what else do we have there? We have the next one. We want to find theta. So this theta will be omega I times t plus half alpha t squared. Like that. And the last one, theta again, will be omega I plus omega final over 2 multiplied by t. So t hasn't changed. So we've substituted for our displacement. We have angular displacement represented by theta. Remember, theta is in radians. Theta is in radians, and omega is in radians per second. T is in seconds. So that's how you interchange to this domain. So besides, let's see if we can apply any of these equations to answer the question we have on the screen. So at t equals to 0, a wheel rotating about a fixed axis at a constant angular acceleration has an angular velocity of 2 radians per second. 2 seconds later, it has turned through 5 complete revolutions. Remember, revolution is 2 pi. That's what you need to pick from this question. What is the angular acceleration of this wheel? So you need to find the angular acceleration of this wheel. You are given the time, 2 seconds, the displacement, angular displacement, which is 5 times 2 pi. So we've got theta equals to 5 times 2 pi. Five times 2 pi radians per second. Radians, just radians. Then angular velocity. Constant acceleration has an angular velocity. So the initial omega I is equal to 2 radians per second, like that. Time t is equal to 2 seconds. So we need to find alpha. We need to find alpha. So if we are given s, it means we use theta. We use this equation number 3. theta is equal to omega I times t plus half alpha t squared, just like that. So everything is given. Omega I being 10 pi, t being 2 plus, omega is 2, this is the 10 pi, equals to 2 for omega times 2 for t plus half alpha times 2 squared. So already alpha is the only unknown. It means we have 10 pi minus 4 multiplied by 2 over 4. So this is equal to alpha. So if we multiply by this 2 here in the denominator from the second term, and we divide by 4 there, we just take everything to the other side and remain with alpha on the right hand side. So 10 pi minus 4 over 2, which is 5 pi minus 2, is our answer. 5 pi minus 2. Let me see if my calculator can give us that. 5 pi minus 2. 13.7. So to two significant figures, that's 14 radians per second squared. So that's the only closest answer there. 13 is won't be correct. So it's 14 because it's 13.7. You present it to two significant figures per second squared. So that should be simple. You cannot afford losing marks for such giveaways. Then the next one related to it, there's nothing there. Now we can jump to number 13. Number 13, similar. We collect our data. So given quantities, first we have an initial, so a wheel rotates about a fixed axis again with an initial angular velocity, omega I of 220 radians per second. Then during a 5-second interval, the angular velocity increases to 40. So omega final is 40 radians per second. And the time during which this happens being 5 seconds. Assume that the angular acceleration was constant during the 5-second interval. How many revolutions does the wheel turn through during the 5-second interval? So we want to find theta. And from theta, we find how many revolutions that value of theta is. So what we do, omega final, omega initial, and t. So theta is equal to omega final squared minus omega initial squared. We don't have theta is what we want, over 2a. We don't have alpha. So which equation do we resort to here given these quantities? Omega final plus omega initial over 2. Yes. So the fourth equation is becoming handy. Omega final plus omega initial over 2 multiplied by t will be equal to theta. So it actually makes things easy because we don't need to find alpha first and then plug into the other equation. Remember, time is also of essence in your writing of your exams. So you better identify some, not really an easy way, but something that saves you time. But anyway, it's an easy equation. Omega final, 40, plus omega initial, 20, everything after adding divided by 2 multiplied by 5. So our theta will be equal to 60 over 2, which is 30 times 5, 150 radians. 150 radians is equal to, revolutions will be theta over 2 pi. That's the number of revolutions, which is 150 radians over 2 pi radians per revolution, per complete revolution. So that gives us 125 over pi revolutions. 125 over pi revolutions. So let's see if we say 125 and divide that by pi. 39.78. 39.8 revolutions. Do we have anything close to that? So the 0.8 is not counted as a complete revolution. We have 39 revolutions there. Let's see if that will be correct. Oh, it's 24. Wow. Wow, what did I do wrong? What did I do wrong? 150 over 2 pi. Oh, 75. Why did I say 125? Sorry. 150 over 2 pi. This is overexcitement, so you have to be careful and not fall into the same trap. This is 150 over 2 pi. Why did I even want to reduce this? 150 over 2 pi is 24, yes, 23.8. Or otherwise it's 75 over pi. So I divided 150 divided by 2, then I don't know why I said 125, sorry guys. If I say 75 over pi, that's the 23.8. 23.8. So you better not try doing the mental like I'm doing here. But anyway, the revolutions, we have 24 revolutions there. It's actually correct. It's 24 revolutions. So the correct answer is B and not E. So yeah, that's just an error that one needs to avoid. Anyway, the next question, question 14, a wheel rotating about a fixed axis, again, with a constant angular acceleration. So this time we've got acceleration, alpha, is equal to 2 radians per second squared. Turns through 2.4 revolutions. So theta equals to 2.4 pi, 2.42 pi radians. I've converted to radians already from revolutions, and the time is 2 seconds. The time is 2 seconds. What is the angular velocity at the end of this? So we want omega phi now. And now we're gonna do theta equals to omega initial t plus half alpha t squared. But we don't have omega initial, but we know that theta is also equal to omega final t minus half alpha t squared. So this is the other way in which we can write this same equation based on omega final. Considering we want to find omega final, we're just eliminating the process of finding omega initial first and then plugging it into this equation, and then going from there to find omega final according to equation 1, which says our omega final is omega initial plus alpha t. So we don't want to go the long way. Always choose that easier and shorter way to save ourselves time and minimize errors. So now, based on that equation, theta is equal to 4.8 pi equals to omega f, and we said t is 2 seconds minus half. Alpha is 2.0, and t is 2 squared, which is 4. So that means we've got 4.8 minus plus 4, 4.8 pi plus 4, everything divided by 2 is equal to our final velocity. So which means we've got 2.4 pi plus 2 being the final velocity. So we evaluate that again. Where is my calculator? Right. We said we have 2.4 pi plus 2, and that gives us 9.54, 9.5 radians per second is equal to our final angular velocity. And 9.5 is A. 9.5 is A, and that should be the correct answer. Okay. So that is what we have with regards to motion about a fixed axis. I'm sure you're gonna remember that. Next time you have questions on this, you should be able to answer them without any problems. So take note, it is also important to revise. You've got a lot of practice questions from your practice for marks and also from your touch tests. So you can look into those questions if you didn't do well on them and see what you can correct from there. Okay, so now an angular speed, the angular speed of the minute hand of a clock in radians per second is, so angular speed is omega equals to d theta dt. So d theta in radians will be the displacement, which is within a minute, and within a minute the displacement will be just 1 over 60, right, for the 60 minutes that are in an hour, right? So remember, for the minute hand to go through the whole cycle, it has to go 60 minutes. So the rate at which it is going through that 60 minutes is when it goes 1 minute, right? 1 minute to have moved a fraction of 1 over 60 of 2 pi, right? So if maybe we could just put something like a clock there. Okay, ideally that would be 12, 6, 3, 9. Then you've got your 1, 2, you've got your 4, 5, you've got your 7, 8, and your 10, 11. Okay, something like that. So we've got 5 minutes in between 12 and the next mark here. That will be 5 minutes. So you've got 5, 10, 15, 20, 25, 30 until you get to 60. So each time it's moving, it's gonna be moving 1, 2, 3, 4, and that's 5, right? So for it to move 1 minute, it moves that 1 minute in 60 seconds. So that means this is just a fraction, 1 over 60. Let's see if I'll be able to. Right. Then to go to that point. Okay. So that region there, to get just a 1 dot, or when it moves 1 minute, then it will have moved 1 over 60 of 2 pi. But it does that in what? In 60 seconds. In 60 seconds. And this is 2 pi radians. So already that's 2 pi over 3600 radians per second. That's our speed. So that's 0.00056 radians per second. Or otherwise it's 1 over 1800 pi. Do we have a pi there? Yes. Pi radians per second. Or 1 over 1800 pi radians per second. Okay, that should be a simple one. So it's a matter of at least just reasoning, understand the given situation or the given case, and just try and apply what you already know. So here we've got pi over, okay, so that's pi over 3000 2 pi over 3600 2 pi over 3600. Did I put it right? which is pi over 1800. Okay. The fraction there, why did I see something different? Was it expressed? Okay, without the pi there. Yeah. So that's yeah, that's right. 0.00056124. Yes, 56 pi radians per second. Okay, so everything is all right. That's basically our omega, and for this question, one of the solutions there should be correct. I just don't know which one. But whatever it is, it should be 1 over 1800. Okay, so I chose the correct one. I don't know anyway what was supposed to be there, but definitely should be pi over 1800, not any of D, E, C, or A. So, okay, so that's it about this part. So we can just skip to the next part on static equilibrium. Let's see what we have on static equilibrium. Linear momentum and collisions. What happened to that? Okay, continue. All right, we'll just look at a few questions from there. So I'll start from here. Okay. So remember conditions for equilibrium as well for this part of the unit. It is important to just know what you're dealing with at any given time. So if you are seeing, I hope you can see and hear the audio clearly if you are joining us. This is just for your revision, so just to help you with your studying and keeping up in case you missed something along the way. Okay. So we're just gonna continue on a static equilibrium. So conditions for equilibrium, remember your conditions for equilibrium, the net force, external force or external forces should be equal to 0, and the net momentum, total momentum, which is clockwise and anti-clockwise, should also be equal to 0. That is the total torque, which is a product of your force times the perpendicular distance to the point of action, which is the point of rotation. So those are the two main conditions that you need to look out for as you deal with these questions. And remember, if you are dealing with any force on a rotational system, what you are supposed to balance also are the rotational moments. So those moments you need to multiply by displacement. It is important to remember displacement in your equations. That's the error or the trap that many usually fall into and miss that part. It gives you a wrong answer at the end. Okay, so a horizontal uniform meter stick supported at the 50 centimeter mark, which is something like this. So if this will be a 50 centimeter mark, and starting from 0 to 100, there's a mass of 0.5 kg hanging from it at the 20 centimeter mark. So if we take 20 to be there, and we've got a mass 20 kgs, 20 times gravity, right? And a 30 kg mass hanging from it at the 60 centimeter mark, right? So 10 centimeters away is another mass hanging, which is known to be so this is actually 20 centimeters, and the mass is 0.5 kgs, 0.5 g. 0.5 times G. And this is 0.3 times G, the gravity. So I've put the weights there for the force. Determine the position of the meter on the meter stick at which one would hang at that mass of m kgs. So obviously by moments, if 0.5 is 30 centimeters away, 0.3 weight mass is 10 centimeters away from the pivot. It means we need to balance this because the moment there is smaller. We need another mass that would counterbalance, which is m times g, at a distance x away from the pivot. X away from the pivot. So what that means is for our moments, moments, we've got clockwise moments and anti-clockwise moments. So the moments due to the mass on the left will be 0.5 g multiplied by 0.3. Remember, we're 30 centimeters away. If we were at that mark, this is 30 centimeters. So that's 0.3 meters. Should be equal to 0.3 times gravity multiplied by 0.1 meters plus m multiplied by 0.5 plus x meters. So why 0.5 plus x? No. X minus. If we want to find x, then that's x minus 0.5. This distance x is x. If we want x in centimeters at that point, so it's x minus 0.5 meters. So this 0.1 is 60 minus 50. That's why we get 0.1. This 0.3 is 50 centimeters minus 20 centimeters, which is 0.5 minus 0.2. So we've said x minus 0.5 so that we directly get the position on the meter rule. So now if we take the calculations there, 0.5 times 0.3, it gives us 0.15 multiplied by gravity minus 0.03 multiplied by gravity equals to m times x minus 0.5. Okay, so because we know the value of g, we can calculate that 0.15 minus 0.03 multiplied by g. Okay, let's see what's happening there. 0.15 minus 0.03 multiplied by g equals to m times x minus 0.5. So this is 0.12 multiplied by g over m plus 0.5 equals to m. Okay. Equals to x. So we divide by m, then we add 0.5 on both sides to remain with x. So that's what x is. It's 0.12 meters. So that's in meters multiplied by gravity. Multiplied by gravity divided by m plus 0.5. Everything. So this is everything in meters. Is equal to x. So here, what do we have? 12 over m plus 50, so it's in centimeters. Did they leave, what happened to 0.3 kgs force? Okay, so this is mg, there's g there. So the g goes away. Remember, this is mass times gravity again, so the g at the end will simply go out. So we simply don't have g in that expression. So if this is in meters, it means in centimeters multiplied by 100, 12 over m plus 50 centimeters. So b is the correct expression for x, 12 over m plus 50. So this is what I was saying in terms of not omitting any of these factors in the calculation of moments or of your torque. So remember, it's always force times displacement, from force to pivot, force times displacement, and force times displacement. So if the g is not there, then that's not a force, that's just a mass. So you need to be extra careful with that. Okay. So that's a good thing. You have seen how easy it is to just miss the mark by just omitting one simple thing there. But anyway, that's the expression that you would want for that question. Then the one for an inclined beam, or an inclined beam lying or resting on a vertical wall. A uniform beam having a mass of 60 kgs and a length of 2.8 meters. So sorry, if you have any questions, please, you can just type on the chat. You can just type them on the chat box. I'll be able to help you if you are here with us. So you can just chat with me here. Then we'll be able to talk. All right. So I'll just go over to the next one. You are familiar with this kind of question. A uniform beam having a mass of 60 kgs. So this is the kind of picture we have. And then we have a beam. And its mass is 60 kgs. I think the angle is in the diagram there is 40 degrees. Then the length of the beam is 2.8. So 2.8 meters. So it's held in place at its lower end by a pin. So we've got a pin there at point P. And its upper end leans against a vertical frictionless wall. So this is our vertical wall. If it's frictionless, what does that mean? What does that tell you? If you're told the wall is frictionless, it means there's no yes, there's no friction, but also the force acting from the point of contact there will be acting normal to the surface. So we've got that force there acting from that point. Because there's no friction, it acts normal. So we'll call this F wall, right? So by balancing these forces, it means there is no component upward, because friction will give an upward component, and as a result, the net force acting from that point of contact will be at an angle other than a 90-degree angle. Okay, so that's the importance of the friction that is being stated there. So from here, we've got a component that's upward. We can call it Fp in the y, and we also have a component that's Fp in the x, such that Fp is the resultant force at P. We've got a resultant there, Fp. Okay. what is the magnitude of the force the pin exerts on the beam? So we want to find FP at the end of the day. We want FP. So Fpx by virtue of equilibrium there should be equal to Fw, and Fpy should be equal to the weight of the beam. So the total upward and downward forces should be equal to 0, meaning Fpy minus W should be 0. Then the total horizontal forces also, Fw and Fpx, should also be 0. Right? So now Fpy is easy to find because this is 60 times 9.8 newtons. But Fw, we need to find moments. We need to find moments there. So for our moments, we'll take moments about P. We have to consider moments about point P so that we eliminate, or we don't have anything to do with the FP in our calculation for moments. So what do we do? Okay. So here are moments about P. Moments about P. So we've got 60 times 9.8. So the weight multiplied by L over 2 is the counterclockwise force. Should be equal to the clockwise force, the moment, the clockwise moment, which is Fw. Actually, this is a cos theta component, so we can have W cos theta. Okay, so the one perpendicular to the weight is that component there. That component is W. Remember that angle becomes theta there. The moment you make your beam lie horizontally on the ground, this component W cos theta, the W cos theta here, will simply also be perpendicular to the ground. So if you take your beam down this way, you'll find that this component will align with where the weight is. So if you take it back up, the component that was initially along the 60 faces with the component into the wall at an angle theta to the horizontal, because you have just raised the beam at an angle theta, so it makes that angle between the vertical and the component that is perpendicular to the beam at theta degrees. So the angle between them is theta there. So W cos theta is perpendicular at 1.4 from the pivot. So that's why we have W cos theta times L over 2. Whereas we have here, this is still theta, but then we have a component that's perpendicular is the one that we want, and that would be Fw sine theta. So Fw sine theta multiplied by L is the other moment. So because L is 2.8, W is 60 times 9.8 times cos of 40 times L over 2, which is for 2.8 divided by 2, that's 1.4. Should be equal to Fw times sine 40 multiplied by 2.8. So divide by sine 40 multiplied by 2.8, both sides. We have Fw being equal to to the 30 by 9.8 times or divided by tan 40. 30 times 9.8 divided by tan 40. So this is 30 times 9.8 over tan 40. What happens? Let's see, 30 times G divided by the tan of 40, 350.376, 350.376, 350.376 newtons. So this is the magnitude of the FW, which is the same as FPX, 350.376 newtons. So for us to find FP, it's now simple because we've got the X component and the Y component. We square them and add, then find their square root. So this is the root of 350.4 squared plus 60 times 9.8, that's 5 point something. So let's see what that is. 60 times 9.8, 588 squared. So the square root of, I'll find the square root of 588 squared plus 350.4 squared. $684. FP is therefore 684.5 newtons. Okay, I hope we did everything right. If we did everything right, then we should have that within the possible answers. 0.68 kilonewtons. So that's the closest. That's the closest. Okay, so 0.68 kilonewtons, that's fine. So that's 684 newtons or 0.684 kilonewtons, 0.6822 significant figures. So that's basically what is important with the beam. Your components, remember, it's force times the perpendicular distance from the line of action of the force to the pivot. So in this case, we have our force at an angle theta. That's an angle theta to the component that makes a 90-degree with the beam, or with the line of action to the pivot. So with that, we would have to use the components. That's why we used cos theta and sin theta components in this case. Okay, so let's take a short break. I will be with you in a moment. Let's take a short break. Our next question will be question 12. It's a simple one. You can just look through it while I address a few things here. Okay, we are back. We are back from our short break. I hope you guys were able to just follow on what we have been. Okay, Aluve, why did you retract your message? Okay, I hope probably you got answered if that was a question. But anyway, let's proceed. Let's proceed. What do you think about this question? It's a simple one. The diagrams below show forces applied to a wheel that weighs 20 newtons. The symbol W stands for the weight. In which diagram or diagrams is or are the wheel not in equilibrium? So in which case or in which diagrams will the wheel not be in equilibrium? So in case A, if we look at the translational forces, the net force there is 0 because W is 20 newtons. But the torque or the rotational forces, clockwise moments. Okay, so look at a horizontal forces translational. The total 10 plus 10 is 20 to the right. There's nothing to the left to counterbalance it. So already the condition of equilibrium is not met there. But if we look at the moments, 10 newtons acting a distance equivalent to the radius away from the pivot, and another 10 from the top at an equivalent distance in the opposite direction, they counterbalance. So rotationally it is in equilibrium. But the only problem is the horizontal equilibrium is not met in the horizontal direction. So A is not in equilibrium. Then for B, vertical forces balanced, horizontal forces balanced, but rotational forces, they are both clockwise. So rotationally, or in terms of moments, there is no equilibrium there. B is not in equilibrium. Then for C, upward and downward, 10 plus 10, 20 versus the weight, it's balanced. Left and right is balanced. There's no force in either direction on the horizontal. Then for torque, moment, clockwise moment and anti-clockwise moment balanced. So C is in equilibrium fully. And D, moments are not balanced there. Vertical forces not balanced. So A, B, and D are not in equilibrium. So A, B, and D are not in equilibrium. So that's a simple one. It's just to see if you understand your different conditions for equilibrium. Okay, so a different one is question 13. The figure shows a uniform horizontal beam length of 10 meters, mass 25 kgs. That is pivoted at the wall with its far end supported by a cable that makes an angle 51 degrees. So I'll try and draw this one for you. Horizontal beam, like that, wall, okay, and 51 degrees. Okay, the beam is 25 kgs. The length is 10 meters. So hey, how is it pick? Not yet. In 30 minutes. Okay, sorry about that. So anyway, we are saying the mass there is 25. We have 25 kgs, 25 kgs, 25 times g. So that's the weight, 25 kg from the center. Anyway, that's where we would assume all the mass of the beam is concentrated. So because it's a uniform beam, I think that's why it is important to have this in the description. It's a uniform beam. So because it's uniform, it means the mass is evenly distributed, and most of it will force the weight will act on the center as if that's where all the mass is concentrated. So that's how it works. Anyway, the angle is 51 degrees. We can see according to that diagram, it is supported from the far end, and then a person of mass 60 kg stands 3 meters from the pivot. So which one is our pivot in this case? What is the tension in the cable? So it is pivoted at the wall, so we can call that our pivot. Then 3 meters is some guy there, and the mass of that guy is 60 kgs. So now we want the tension that supports all these forces. Okay. So what does that mean? That means if this is 30, say, what is that? How much? This is 3 meters. So it means if we take clockwise moments, it will be 60 times 9.8. Remember, it's a force with the weight acting 3 meters from the pivot, plus the 25 multiplied by 9.8, which is the weight acting 5 meters from the pivot, should be equal to the tension sine 51. Why sine 51? Because the component that's perpendicular to the beam and giving us an anti-clockwise moment will be T sine 50. The tension sine 50, the vertical component of that tension, acting at 10 meters away from the pivot. So if you look at it, the only unknown there is T. So it simplifies the problem. That simplifies the problem. So we're supposed to have a diagram there. I've already drawn it for you. Let's calculate and see what we get. So I'm just gonna put the open bracket. We've got 60 times 9.8, 60 times 9.8 times 3 plus 25 times 9.8 times 5, then divided by 10 sine 51. So everything there is divided by 10 sine 51. So this gives us T equals to 384.6 newtons. So this is the value of T we get. And we can check. Let's check. 384, 0.38. Okay. 0.38 kilonewtons. That's correct. So that's another simple way of dealing with the inclined beams in static equilibrium. Okay. Now, the next question says, Ng says that an object is in equilibrium if the net torques about the center of mass is 0. And Robbie says that an object is in equilibrium if the sum of external forces is 0. Which one of either is correct? So both are correct. An object is in equilibrium if either condition holds. Is that true? If the net talk about the center of mass, so what if it's about the end or any other position? Is that not true? So you can think about it. But Robbie says that an object is in equilibrium if the sum of external forces is 0. Okay. So are they both correct? Are they both wrong? So neither is correct. Both conditions must hold simultaneously. Sure. I don't know. Or C says neither is correct. The net external force and the net external torque about n axis must be 0. D says neither is correct. An object is in equilibrium only if its velocity is 0 in all coordinate systems. Okay. And E, both are correct. If the sum of the external forces is 0, the net torque about n axis is automatically 0. And vice versa. Okay, that's a weird one. But anyway, let's eliminate. I'll start with E. The sum of the external, about the both being correct, I'm not sure. But the sum of the external forces, if it's 0, the net torque about n axis is automatically 0. That's not true. And the vice versa is not true. So E is out. D says neither is correct. I am not sure about that part, but if it says an object is in equilibrium only if its velocity is 0 in all coordinate systems, that's not true, because we can have what we call dynamic equilibrium when all the forces are, net forces are 0, but the body is still moving, so the velocity won't be 0 then. So a condition for equilibrium, forces can balance, but the body is still moving at constant speed or velocity. Then neither is correct. The net external forces and net external torque about any axis must be 0. The net external force and net external torque about any axis, I think net external force and net external torque about any axis must be 0. I'll go about with this. Let's see. Neither is correct. Both conditions must hold simultaneously. So the condition to say external torque about the center of mass there eliminates what Angie says. It's not about the center of mass. So this is the part where this statement is wrong. Just the center of mass. It's just the whether we consider the moment or torque about any given axis. If it's balanced, that moment should be 0 about any axis, right? So, and then the two of the conditions should apply. So if this one states 1, then without the other, then it still makes them incorrect. So the conditions there should hold simultaneously, yes, but not the condition about the talk about the center of mass. That one is wrong. The condition for net moments being 0 and net force being 0, and the net moments are just about any axis. So C would be the most appropriate one. Both are correct, and an object is in equilibrium if either condition. It's not about either. If both conditions are met, both conditions should be met. So that should be C. That should be C. And the last part of this one, John is carrying a shovel full of snow. Okay. The center of mass of the 3 kg, let's see if we can, okay, with the handle there. So the center of mass of the 3 kg of snow he is holding is 15 centimeters from the end of the shovel. Okay, so this ideally will be 15 centimeters. So there's one hand holding from there. So that will be one hand gripping with an upward force. And there will be another hand there. So that is the pivoting hand, and the force starts balancing. And then this is the snow with that mass there acting 15 centimeters from the end. Okay, so he's pushing down on the opposite end of the shovel with one hand. So this is the end pushing down and holding it up at 30 centimeters from the end. So double that distance. 30 centimeters is the other hand holding up. Ignore the mass of the shovel. Sarah says that his hand pushing down on the shovel must be exerting a greater force than the hand pushing up. So this is force from the hand, force up. So Sarah says force B is greater than force P. Okay. Whereas James says it is just the reverse. And James says FB is less than FP. So which one, if either, is correct? Okay. Which one, if either, is correct? So from here, what can we say? What can we say from the given information? So remember, the force at P for the net force should be equal to the force at B plus the force at S in terms of translational forces. So the net translational forces should be equal to 0, meaning the upward forces should be equal to the downward forces. So this is up and this is down. The two should be equal, right, before we start with the turning effect. So if that's the case, then the force at P is definitely greater than the force at B. The force at P is definitely greater than the force at B, because FB plus FS is equal to FP for our translational forces. Then we can now also apply the moments. You would know that the force at S is depending on that distance anyway, which we don't know. If that distance is greater than 30 centimeters, then the force at B will be less than the force at S. But already we have ascertained because we want to compare with P. So anyway, which one is correct? Sarah says that the force at the pivot is greater than the Sarah says the hand pushing down on the shovel is exerting a greater force. So for Sarah, the force at the end from B is greater than the force at the pivot. So that's Sarah. So this one, he says the correct one is Sarah, because the hand pushing down must exert a greater force to match the torque exerted by snow. No. The hand pushing down cannot exert a greater force. We have already ascertained it from there. James, because depending on the location of the axis of rotation, the hand pushing down can counteract the torque exerted by the snow. No. So the James could be correct, but the reasoning there is not proper. C says James, because the hand pushing up must exert a force that equals the sum of the force of the hand pushing down and the weight of the snow. I think I like that one. C. James, because both B and C above are correct. No. E, neither, because the hands exert forces of equal magnitude. So let's check if C is correct. If C is correct. So James, because the hand pushing up must exert a force that equals the sum of the force of the hand pushing down and the weight of the snow. Hand pushing down and weight of the snow. So that's correct. So we're done with this part. I'll quickly go to the last one. Which is on universal law of gravitation, but I'm just gonna take a 15-minute break. So I'm just gonna stop this stream and then I will resume. That will be a very short one that I'll take after the coming 10 minutes. So at 10 past 12, I'll be resuming. So see you in a moment. Don't go very far.